introducing me. I'm one of the co-organizers of this Climate Change 101 seminar series. I'm going to briefly introduce today's speaker and then turn you over to her. We're very pleased today to have with us Deb Niemeier. Deb is a professor in civil and environmental engineering at UC Davis. She's a former chair of that department. She's also director of the UC Davis John Muir Institute on the Environment. I believe she's also vice chancellor of some nature at UC Davis. She's a very distinguished researcher, has more than 120 peer-reviewed publications. In addition to research, Deb's involved in a lot of outreach activities, teaching, and other mentoring activities. What she's going to talk about today is, well, the title is Factors Causing Climate Change in California. More specifically, greenhouse gas emissions, where they come from, and how those emissions are likely to evolve in the future as we change policies and as demographic factors change and so on. So let me give you Deb.
So last night, I have to tell you, one of my daughters came in and she looked at this. Cover and she said, "Oh my God, that is so boring." So I was waiting for the last minute anyway to do this talk, and the true nature of things. This morning I got up and I was sitting. Okay, this is really boring. What am I going to do? At the opening slide, and so I heard one of my other daughters yell, "Well, what are you talking on?" And I said, "Climate change and how humans help it along." And she yelled, "Tell them about my sweatshirt." And I had to laugh because she just got this new sweatshirt that she really likes. Okay, so it's white, which has been bleached. It's from Paris. It was shipped airmail. And so I said, "Oh my God, if I had to talk about that for too much, that would be a real icebreaker for drivers of climate change. A bleached white sweatshirt shipped in from Paris." So what I'm going to talk about today is, this is a storyline. And essentially, I'm going to talk about how anthropogenic activities you and I participate in as a society and as a community, help to drive or influence climate change. And I'm going to start with the globe. I'm going to tell you what's happening globally and how the models work and why we know what we know. And then I'm going to move to the United States and tell you a little bit about what's happening there. And then about the last half of the talk, I'm going to talk about California and what's happening in California, how we're growing and what ways this is pushing our emissions boundary, greenhouse gas emissions. And then I'm going to end with sort of a small anecdote about two houses in Davis. And so we're kind of gonna come down from the world all the way to someone's house in Davis. To start with, this is the schematic framework that the IPCC uses to analyze the models to figure out where climate change is going. And essentially, they look at the anthropogenic drivers, the drivers that are created by human systems, and their linkages. And in the third IPCC assessment, we had enough information available to us to go clockwise in this diagram. And in other words, we were able to talk about how climate change was going to impact natural and social resources. By the time the fourth IPCC came out, which was the one that just came out, we had enough information to then start talking about the counterclockwise direction in this schematic framework. And that is that we can begin to sort of analyze the different pathways that society could take as it grows and the risk that each one of those pathways presents to us as a global society in terms of how much climate actually changes. All right, so by pathways, what I'm talking about is how we'll develop in the future. And the way that the models are run from the IPCC is they're run using a series of a set of families of different scenarios. And each of the scenarios explores different ways society could grow and could develop. And there are some major inputs to the model that are based on human sort of activity. And that's in the global sense, it's the demographics. It's so how the population is changing, the technological changes that are forecasted to occur, and the economic changes. And the outputs of these models are greenhouse gases, and that's what tells us how much temperature is likely to rise. So there's probably 40 or 50 different scenarios that have been run, but they all break down into about 4 families, okay? And so I'll show you these families. The A1 family, which up there has a D and a B and an F. The A1 family assumes a world in which everything grows very rapidly. A global population peaks in mid-century, and we have a whole bunch of new technologies that are rapidly introduced. And the A1F1, which is the blue line, says society works off of fossil fuels. The A1T says non-fossil fuel-based energy resources are discovered and put into play. And the A1B looks at what happens if there's a balance across all the resources. The B2 or the B storyline has the same global population, but with more rapid changes in the economics, world economics, towards service information society. So it moves us in that direction much quicker. That's the B1. The B2 storyline describes a slower population growth, sort of intermediate, and it emphasizes that lots of local solutions. Local in this context means each country takes on some solutions to economic and social and technological or environmental sustainability. And then finally, the A2 storyline, it has high economic growth, high population growth, and very slow economic growth, and very slow technological changes. And so whenever you see these diagrams about how greenhouse gas emissions are projected to occur, they're really based on these family of scenarios. Now, it's really important to understand that these scenarios don't represent any likelihood of outcome. They just represent the pathways for which we have some degree of control about how we begin to evolve as a global community. All right, so in 1970, since 1970, greenhouse gases have increased about 80%, and the rate of growth was much higher. You can see from this figure between 1995 and 2005, and it was in fact even higher than the previous period. And the largest proportion of this growth has come from energy supply, transport, industry, and residential, with smaller amounts from commercial, residential, forestry, and ag-related emissions. And these sectors, transport, residential, commercial buildings, energy supply, are fueled, again, by global income wealth, which is the GDP, and also by population growth, global population growth. Okay? Now, if we look at how combustion and industrial processes are broken down, you can see the effect of the drivers in these in this plot where everything's been normalized to 1990 here. Over time, global emissions, which is the black line, have increased, and you can see that it's pretty well associated with both the global population, which is the red line, and the per capita GDP. That's the income wealth that has occurred globally. And that GDP is the sort of, it's supposed to be orange, but you can see it up there at the top. And just to remind everybody, GDP is sort of a way of measuring the size of the world economy. And in this case, I'm showing GDP on a purchasing power parity. What that means is it normalizes across country to equalize the purchasing power of the currencies. And I've tried to give you a sense about where purchasing power parity occurs. And the darker it reflects greater purchasing power. Darker is higher. And the other thing I want to point out on this slide is the last few years since 2000. Here you can see that there's this sharp uptick in both the global energy and global carbon intensity. Slight uptick. And this in turn has resulted in what is believed to be that sharp increase in the global CO2 emissions on the black line. And I'm going to come back to this in a minute, and I'll show you just sort of where I'm talking about there with the CO2. Okay, so at this point, what I hope you sort of have gotten is that we're really talking about potentially 4 major global drivers of CO2 emissions or greenhouse gas emissions. And those are population in the global sense, income, wealth, GDP in this case is how we measure it, and changing carbon and energy intensity. All right, now the global CO2 flux, you can break it down into different components, and some of these will look very familiar. There's 7 different major categories, and the first 3 represent these combustion processes at a national level, all aggregated to the globe. So those first 3 are the things we would normally see, you know, big parts normally see with things like transport and things like energy supply. And they are by far the biggest source of CO2 emissions in the world. All right, now if we look at fossil fuel CO2 emissions over time, right, you can see that for everybody, CO2 emissions are increasing over time. If you look at the tails of the developing countries, you can see this, again, this slight uptick that I showed you on the earlier diagram, and it's mostly thought to be a function of basically a sharp increase in income wealth, which is the orange line here, and decreasing carbon and energy intensities associated with GDP. And this is in regions like China, okay? So globally, this sharp uptick has been associated with really fast development in a few countries. Okay, now if we look at what happens with the US, you can see a little bit of a different pattern here. What you see is that we've managed to sort of decouple the energy intensity of our income wealth. In other words, we can grow, and it doesn't necessarily mean that our energy use is going to increase. And you can see that global CO2 emissions have increased more or less as a rate of a function of population. So as our population grows, so does our CO2 emissions, all right? Which brings me back to this slide. If you look at the changes on this slide over time, what you see is that CO2 emissions from fossil fuel increase over time, and also the rate and amount of land use changes has increased over time. And this is where I'm going to come back to this a little bit, to this slide now for California, or for the US. If you look at the bottom right, we're back to transport, commercial buildings, industry, and energy supply, really driving forces. And they account for roughly 70% of CO2 emissions worldwide. Okay, so let's look at these charts by sector, these important sectors I've been talking about. I pulled these together last night, and hopefully I didn't make any big mistakes, but from this you can see some basic patterns emerging here. Per capita energy use in the US is generally going down, except for transportation, okay? And the graph on the top right supports this notion that we can decouple energy consumption and GDP. In other words, we can grow without necessarily assuming that we're going to consume more energy on a per capita basis. And the bottom graphs are really telling in the sense that we can see that the per capita rates are generally going up, but slowly, and carbon intensity in residential and commercial sectors is going up. And carbon intensity in transportation fuels has largely stayed flat. Although I did hear, you know, via some gossip that the White House might be willing to give us a holiday gas tax permanently if we agree to give up fuel standards. So how goes California? All right, this is a big question. Here you can see in the plot to the left that CO2 emissions are definitely increasing over time, and that they're projected to increase. And you can also see the goals that are on there. And then you can see from the pie charts that California has both some similarities and some differences from the global numbers I gave you earlier. Combined, California's residential commercial CO2 emissions aren't really that different from the global numbers I gave you. We have about 9% energy greenhouse gas emissions by that sector versus about 8% globally. Energy supply is roughly about 25% for both the global and the California numbers, and industry is really close as well. Where we radically differ from the global numbers is in transportation and the land use sector. And in transportation, we globally, there's about 13% of CO2 emissions. In California, we produce roughly 8% of our CO2. You can begin to see how these drivers are really become forcing factors that we need to think about how we're going to deal with them in the future. And if you look at our two biggest sectors, so transportation and energy, you actually see some of the same patterns that we've seen earlier. This is transportation, and you can see that VMT is increasing at a faster rate than our population is increasing. And if you remember from the earlier diagram, you saw that the VMT per capita was going up much faster than the population. And here's another way to look at it. Now, the two sectors, energy and transportation, account for about 65% of the state's CO2 emissions. So these are important sectors. And then if you look at how residential, commercial, industrial, and agricultural consumption is going by sector, what you can see is that residential and commercial energy consumption is going up quite a bit, whereas industrial and agriculture is sort of holding flat over time and projected to hold flat over time. Okay? So let's turn this into a per capita basis. Here's what's happening on a per capita basis, right? And you can see that VMT is going up much faster than the rate, and then you can see that statewide energy consumption has generally gone up, but on a per capita basis is expected to level off. And in part, this reflects the state's emphasis or energy policy on loading order. And the energy demand in California is met in what's called the loading order. And the first priority is that you meet new energy demand with increased conservation and energy efficiency. Then you meet it with renewables, and then you meet it with capacity expansion of your power plants. So by doing this loading order, on a per capita basis, we're going to level off. But you can see our VMTs just taking up. Now, in part, the loading order has helped hold down the carbon emissions from energy, from power plants, but it's really important to know that we're not on track to meet the goals. There was a 20% renewables in the energy mix that was mandated in SB 1068 for the power plants, and 33% by 2020. And so 20% by 2020. And in the last integrated energy report that came out in last fall, so about 6 months ago, the renewables were at about 11%. So we're not on track. We're probably not on track to make the 20 by 2020. So when you look at this is probably a somewhat optimistic profile of where we're going to go. And to some degree, we're increasing. What's happening is we're increasing slightly faster in energy use on a per capita basis than our population, but we're using conservation and energy efficiency to bring it down to just increasing at the rate at which population is increasing. Population is increasing about 1.3% per year is what it's projected out. So that means overall we're increasing our energy use by roughly 1.3% per year. Okay, so and to show you this, I forgot I had this. This is the population increase. So you can see from I think it starts at 1980 and goes up to 2020. And then the bars represent the percent change, so about 1.2, 1.3 years leveling off of population change. Okay, so now we're going to get really complicated with the slides, and I'm going to slow down a little bit. Okay, so on a per capita basis, on this top slide, I have two things plotted for you, and these are California counties, and the blue bar represents the percent change in county population, and the red bars represent how much of the state's growth the county actually took between 1990 and 2004. So what you can see is that LA took a great deal of the state's growth. Riverside, Orange County all took a fair proportion of the state's growth. And in addition, so did a lot of the San Joaquin valleys. Those are the little red bars. between 1 and 5% for most of the San Joaquin Valley counties. Okay, and what I want to couple with this with is sort of what this growth has represented on the ground. This is the change in growth patterns or the urban boundaries, the urban footprint in Fresno between 1984 and 2002. And what you can see, and I should also say that Fresno has grown the same amount proportionally as like Alameda or Contra County. So it's not insignificant. And Fresno is the 6th largest city in California, 500,000 people. It's important to pay attention to how these communities are developing. And what you can see is that over time, there was a fairly substantial expansion of the urban footprint. Okay? And this has implications both in terms of how we travel again and in terms of our energy use. So here you can see that the number of households increased the most in the South Coast and in the Valley Desert areas. And you can also see that how this growth is predicted to affect peak demand over time. So this is future peak demand. And this is really important because about 70% of California's population lives in coastal areas right now. But the growth that's anticipated, so the new growth that we're actually preparing for now between now and 2040, is actually mostly going to occur inland, not on the coastal side of the state. So roughly 20 million people is what we're predicting will move to the inland portion of the states. And when you move inland, much higher demand for energy in the form of the summers are much hotter. You're going to run your air conditioning a lot more. And, yesterday I just sat in a talk yesterday about solar panels and evaluation of solar panels. And it was really interesting. I didn't realize that solar panels actually do better in a place like San Francisco than they do in Sacramento because they actually need lots of sun but no heat. So we're actually even developing in an area in which we're going to have high heat conditions. All right. So anyway, you can just see that the demand, especially in the peak hour demand, is going to increase dramatically over the next few years. And just couple this with what I've shown you earlier, that on a per capita basis, we're actually flattening out the consumption curve, right? I mean, I showed you a plot that says we're predicted to flatten it out. And so you can see where we're balancing projected population growth on a per capita basis and trying to match energy consumption as we go along. But what in the bottom line is means 20 million new people are gonna push our energy consumption up. So what is growth in VMT going to do? Well, so here's a VMT per capita, again, for each county. And I know it's complicated, but what I want you to get from this picture right here is that nearly every county in the state, VMT per capita is higher than it was in 1990. Does everyone know why I'm picking 1990? 1990 is the year for AB 32, 80% below 1990 emissions. So whatever you see in 1990 is a very important number because that's where we're all headed for, 1990. Okay? So you can see that nearly every county in the state has higher VMT than what they had in 1990. That there's two exceptions. One is in San Francisco where the VMT is actually less. And then there's one county, Glenn County or something, a small rural county where it's actually flipped the other way as well. Actually, there's several. I see more now, Mono County. So, so you can see that people actually left more than they came in. But basically, all the counties have higher VMT in 2005 than they had in 1990. Now, let's couple it with this one, which is also a little complicated, but it'll kind of show you. I've turned that VMT into CO2 emissions per capita now. So same counties as above, but below is the emissions the emissions that were created in 1990 adjusted for 2005 population, and then the yellow dot is the 2000, what we're actually generating now. So we have to go from the yellow to the top of the black bar. Okay, if you go literally over what AB 32 says. So you can see that we got a long way to go in most counties, right? Big difference. Okay, now I'm gonna do one more thing. I'm going to add these bars here. And the dashed bars represent those counties that took 2 to 5% share of the state growth, and the solid lines represent those counties that took between 5 and 20% share of the state growth. So those were the little red bars on the earlier graph where I was showing you what was happening to population in the state. Okay, now if you stare at this for a really long time, which admittedly we don't have, what you begin to see happening is that there's basically two options we have in terms of VMT. We either have to make a relatively small number of people make a very big change in how they drive, okay? Or we have to make a lot of people make a small change in how they drive. Those are essentially our two pathways. And the reason is we've got a whole bunch of people who moved to LA, but the VMT per capita didn't change that much. And we've got a fair number of people who moved inland, and their VMT changed a whole lot. They were driving a whole lot more. So we either got to make, a whole bunch of people change a little bit, or a fewer number of people change a whole lot. And probably some of both. But that gives you a sense of sort of what's happening with transportation. Okay, so does this really matter? Can we really actually change how things are going? So to do this, what we did was we took 8 counties in the San Joaquin Valley, and we simulated different kinds of growth patterns in the 8 counties in the valley. And we looked at what the change in transportation patterns would be after we simulated counties. And before we calculated the CO2 emissions, before I go through there, I want to tell you sort of each of these scenarios, and you can kind of see what the densities were for each scenario. The baseline scenario assumes that we accommodate the projected population growth according to the general plans of the cities and counties that we used, but we don't allow any expansion of the transportation network. Okay? And then the controlled growth or compact scenario is we say all new growth gets compact development. All gets pushed towards the near to the urban boundaries, within the urban boundaries, and we put them at very high densities, and we don't put any transportation expansion, capacity expansion at all, but we put in the high-speed rail. Okay, so that's the second controlled option. Then the third one is we just let everybody go wherever they want to, and we increase the transportation capacity. We don't give them light rail, but we build everything we need to get them where they're going. And then the as-planned scenario was given to us by some who are doing some work in the county, and essentially we take the way the counties see themselves growing, and all the regional transportation improvements they envision putting in place. Okay, so 4 scenarios. All right, now what you might expect is what happens basically. I've tried to give you the CO2 emissions in the chart to the right, and then sort of a reminder about what's happening with transportation to the left there. And what you see is that basically the CO2 emissions are bracketed on one end by complete sprawl. We let them go wherever they want to, and on the other end where we force all new growth to be compact development. And you would expect those 2 CO2 emissions to bracket. Then what you see is that the baseline, where we don't allow any, has slightly better than the as planned, and that so not putting any expansion in sort of controls the amount of travel that actually constrains it, that actually occurs. But you can see in every case we are way over year 2000 estimated emissions. And beyond that, remember I showed you a chart where everybody in 2000 is much higher than 1990. So we're a long way away. Right now, California has these legislative initiatives in play, and one of them, most notably, I should say, is AB 32, and the executive order S305, I think it is. And basically, they set these climate emissions targets, these reductions that the state is going to accomplish. And so let's see. AB 32 sets 1990 CO2 emissions level by 2020. That's what we're supposed to achieve. And that was the gap you saw between the black bar and the little orange dot. All right. And then S305 sets targets, which are things like sets a target year 2000 by 2010, 1990 by 2020, and then 80% below 1990 by 2050. Okay? Now, what we did was we came in and we said, okay, we can actually figure out what the county's targets would be by coming down to the county level. And so here's what you see. All right. So you see the emissions generated by the four scenarios, and then you see the four targets. And you can see that even if we force all new development into compact growth, which would give you this inner ring range, we're a long way away from meeting the state's targets. Okay, now, I don't consider the low carbon fuel standard, and I don't consider Pavley. So we're a long way away, but even if you consider those two, we're probably 7 to 10 million metric tons away from meeting these targets. So we really, in the state, we really have to think about, if transportation, and going back to this, if transportation and energy are really significant drivers of greenhouse gas emissions, pretty critical that we think about how the pathways we want those drivers to actually take place, because population is just steady for us. It's at 1.3%. It's not a significant driver. We've shown that we can decouple GDP from energy use. So what's driving us is really this sector growth in energy and transportation. And so there's sort of two options that come out of this. And one is that we have to reduce our per capita energy use over time. We've got to come up with ways to actually reduce per capita energy use. Time. And then the other thing is we've got to figure out how to effectively manage and reorient our transportation strategies. And it's probably not going to be new compact growth everywhere. We've got to talk about the gap that remains even after the new compact growth is put in, which was the difference between the gray area and the bullets you saw on the previous slide. And then the last thing, because I want to give a 10 or 15 minutes for questions, the last thing is that if even if we do everything really well, there's still going to be things that we're not going to anticipate. And to show you this, I want to give you a little brief blurb about a study we did in Davis. How many of you are familiar with Davis? Okay, so how many of you are familiar with Village Homes in Davis? How many of you are familiar with Mace Ranch? So Village Homes is it was designed in the 1980s. It was supposed to be a sustainable community, had total energy, 70s, okay, complete energy conservation in mind. The houses have solar hot water systems that they use, and somebody told me it supplies up to 100% of the hot water needs in the summer, and around 50% in the winter time. The neighborhood is highly bikeable, highly walkable. And then Mace Ranch, on the other hand, was built in the late 1990s, early 2000s. It's a subdivision that we're probably all very used to seeing. It's sort of the 3-car garage concept or 2-car garage concepts. And but it's very bikeable, very walkable, friendly, got parks. About 50% of the houses have a solar roof on them. And what we did was we went out and we got energy consumption from PG&E for the houses over a 10-year period. And then we also did a survey in each neighborhood and got about a 50% response. And then we calculated greenhouse gas emissions sectors between the two households. And so here's what you can see. You can see that the mean carbon emissions from household electric and transportation energy consumption per household member. And what you can see is that on the whole, they both generate about the same CO2 emissions. That where somebody saves some money, they spend it actually on high carbon emitting activities, more carbon intense. In this case, they fly more. So in sort of wrapping this up, I would say that that the thing to remember is you always have CC and Rs. So can I answer some questions now? Oh yeah, I have. There you go. It turns out it's not that much older, but you can sort of see you can see some of the basic demographics. So it's not that much different. Yeah. So Mace Ranch on the left, Village Homes on the right. Income higher, not that much higher. Education about the same. Slightly more bedrooms. Sorry? Oh yeah, it would be. Village Homes was built in the 70s. So, I mean, which brings up a very good point, which is if we build right to begin with, it appears to really stay with us over time. So, but, the flip side of how Village Homes was built is that Mace Ranch had the advantage of all the Title 20 forces. So there's some interesting contrast here. Yeah. And I've been working on it for a long time. And they have already cut. So, what do you think about the market forces? No. I mean, it doesn't surprise me lower income households are actually conserving right now. That's exactly what I would expect. But what they discovered is it's slightly different with this gas price fuel spike. We're seeing slightly different behavior than we saw in behavior when the gas crunch happened in what was it, like mid 70s, 80s, something like that. Yeah, so you saw a big drop in in the miles people were driving then. But this time we're actually not seeing much of a drop. We're actually seeing people continue to drive. Okay. Okay. So we should. So the question was: are we seeing less driving as a function of fuel price? Simply put. And right now, what we're seeing is the response to the gas price is not actually causing many of us to drive a whole lot less. Well, whether that continues, I mean, if it goes up to $5 a gallon, we might all take a deep breath and change. But there is a purchasing difference going on right now. So what they're finding is households who bought big SUVs or big cars for what they call style reasons, actual need reasons, those cars are actually being flipped right now at rates that are faster than we've seen before. So that's one response. But the actual driving is not going down. Yeah, I noticed that. It's about 5 years apart. Yeah. Well, I don't think you can. The incomes aren't that different. And if you were to actually, we broke it apart: international trips versus domestic trips, and what we found was there was a difference between international and domestic trips. So, yeah, yeah. Well, I mean, this is called the respending effect. In other words, you save some money because you've actually implemented energy conservation or energy efficiency improvements. You save that money, but what you decide to spend that money on is equally important, right? If you spend it on activities that actually generate greenhouse gas emissions at a more intense level than what you saved it at, it's net. You haven't really done anything. You've done something probably for your household pleasure, but you really haven't done anything for greenhouse gases. Mimi, and then yes, yes, yeah. Oh yeah, I'm sorry. Where the data, the numbers you see back here, right here, were they the same when you normalized on a square footage basis? Although we did notice at the I gave this talk to Caltrans and I actually showed them the footprint of the two neighborhoods. And there's some very big houses in Mace Ranch that have very big footprints. And so as house size goes up, more energy is consumed, which you would obviously expect. Occupation we just categorized as professional versus not, and it's about the same. But what we noticed was a lot of Mace Ranch commuters to Sacramento. But you'll see that in the emissions. That's going to show up in emissions here. Right. You know, everybody always thinks there's a bunch of students. There's very few students in village homes. Yeah. 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 Oh, yeah, that's a good point. So the point is that there might be special circumstances in some of the counties about the population growth. Yep. That's a good point. In the back on the table? Sure. Yeah. Yeah. It's an interesting thing because, you know, when you look at these numbers, you can get distorted if you look at just how much, what the percent growth that the county has actually taken on. Because small, you know, not very many people to small numbers gives a big percent. And that's why I've sort of given you in two ways what the share of the state's growth was, and then what the county population growth was as well. And it's really the state's share of the growth that we have to pay attention. So LA and the Valley took a huge amount of the state's growth in the last 15 years. Those are the areas we really have to look at because those are the areas that have changed a lot. John? Thank you. Yeah, I have those numbers. I haven't actually calculated it out. Yeah. Yeah, I mean, even if you need between 7 and 10 million metric tons of CO2 reduction after you put in Pavley and after which um, increases you know, our miles per gallon tailpipe standards, and then after you put in low carbon fuels. Put those two in, you still got a big gap, and that's the gap that you either have to have technology or we all have to change the way we drive or live. Yeah. Yeah, I know. I read. So the question is how bus rapid transit could help us out of this sort of dilemma that we're in, and I was reading how was it Placer or Grass Valley? Now the buses are completely loaded up coming into Sacramento, And so that's the effect you're talking about. And there's some really good BRT programs all over that are worth looking at. Yeah. Right. Yep. I mean, that's the thing. Yeah. So the issue is, how do we get densities up? Because densities are associated with a reduction in VMT, and VMT is associated with reducing greenhouse gas emissions. So that's the linkage. I think it's really difficult for the state to mandate that all new growth occur in compact development. I think it's unlikely to happen. And so given that we're not going to be able to mandate compact development, the question is, what do you do? What else do you do? And I think there are things like the BRT that you can do if the densities are high enough. A lot of people feel like the only way out of it is technology, be it some sort of vehicle technology. Yeah, no, I haven't thought about that. Air is terrible for greenhouse gas emissions. I mean, I try not to think about air. Yeah. I think that all depends on how housing prices go. I mean, I don't think people locate 2 hours away from their work commuting because of the commute. I think they locate because they're trying to buy an affordable house. So I think the linchpin in all of this is sort of housing prices, and if we're able to build communities in which people can actually afford houses and live in the same place they work or nearer to where they work. But anyway, let me before I come back to you, any other questions? Here, okay. Yeah, a lot of studies saying there's a lot of infill potential. That's correct. Yep. No, no, no. It's all annual. Yeah, it's everything's annual, but it's annual per capita, so it's VMT per capita per year. Yeah. Thank you. Any others? Yeah. So the question is, when was the 20 million sort of inland growth? That's 2040 estimate. 2040. Yep. Any others? Great. Thank you very much.